We're going to finish up today with EM simulation. We have a couple of different EM simulators you can use. Today we're going to take a look at Axiom, our state-of-the-art planar simulator, which is ideal for MMIC module board designers. It simulates horizontal metal and vertical vias. There are two ways of running EM. Either you can work just in the gray box here in the middle of the graph. You draw the project, add ports, simulate, and then use the S parameters in a schematic. Or you can actually ship the layout directly from the schematic layout without redrawing. Ports are automatically added. The S parameters are used back again in the schematic, and all your graphs are updated. And we call this the EM extraction flow. And I'd like to demonstrate that to you right now. Here is a schematic of our stub. Notice instantly that the elements that are purple have layout. The elements that are blue, like the ports, don't. In order to run EM extraction, there are two elements that I need, and the first one is an extraction block. You can get this in a variety of ways. I'll get it from the elements catalog, and I go down here to simulation control. And there it is sitting right there, and I drag it in, and it looks like this. EMDoc is the name of the EM document it's going to create. You need double quotes because it wants a name. It wants a character string. So I'll call it EM stub. The name EM extract, this is going to be used for telling it which elements to extract. Let's come back to that in a minute. For the simulator, you have choices for any simulator you have a license for. EM Site and Axiom are planar simulators. Later this year, we're actually going to be introducing Analyst, our 3D simulator. All of them are driven from the same extract block. I'll pick Axiom. Cell size in Axiom is roughly the smallest triangle, smallest mesh it's going to try to make. It will make it smaller if it has to, but it will try not to. I'm going to set this to about 1/10 of a line width, which is roughly what I find is a good number, and I'm seeing a lot of lines of about 0.5 millimeter, so I'll make it 0.05. Now stack up is the other element we need. To show you the stack up, I'm going to go back to the project browser and up here to global definitions. And we have two stack-ups that Axiom can use, either thick metal or thin metal. The only difference is the number of layers, because when you make non-zero thickness metal, which Axiom can, it will extrude into the dielectric above it, so you might want to make that thicker. I'm going to use thin metal, and I open this guy up, and this is all the information EM needs to be able to create the project. So for example, material depths, the first tab. First grouping here is all the dielectrics it's using, like FR4. Air instantly is predefined. The next block of materials are the conductors that the lines could use, copper, gold, aluminum. We're going to be using copper. The final box at the bottom here would be if we had impedance definitions, so 50 ohms per square painted onto a thin film resistor. We won't be using these for our simple example. Dielectric layers is the stack up of the software, of the project. First layer is always named 1, and they go down in order. You can see we have air, 3 layers of FR4. In a minute, we're going to place our metal on top of dielectric layer 2. So when you put something on metal layer 2 in EM, it will go right here where my cursor is on top of dielectric 2. Down here at the bottom is if you want a top or bottom boundary. Axiom does support 2 boundaries. You don't need to have any conductors on top or bottom. And as a matter of fact, we have an approximate open on the top. And incidentally in Axiom, that's a very good approximation. There is no top. There is no box. It is air going off to infinity. Materials is a tab in which you set names, like here we have one OZCU, one half OZCU. And when you give your line a name, a property like one OZCU, it's going to be made up of 36 micron thick copper. So this is how you define line thickness and what the line is made out of. EM layer mapping is a very important window. It is perhaps the window that people get the configuration wrong on the most. And what it does is, for example, here with layer 1, it takes the drawing layer 1 to EM layer 2, so on top of EM layer 2, made out of 1OZCU, and that was that 36 micron thick copper. If you had a via, like via 1-2, starts on EM layer 2, top of dielectric 2, goes down one layer, that's the via extent, made out of copper. Notice a number of these layers, drawing layers, aren't mapped. Like, for example, PCB 1-2 says none. And that's fine, just don't draw on it in EM because EM won't know what to do with the layer. The other tabs up here aren't used. If I go back to the schematic, we're going to, for stack up, when I click on this, we have a choice of any of the ones in the global defs or in the schematic itself, which we don't have any, and I'm going to pick thin metal. The remaining thing we need to do is pick the elements that we're going to use for extraction, and I'm going to use all of them. So I'm holding down my shift key and I select all of them, except of course for the ports. They have no layout, they're blue. Right click, properties, and under model options, I'm enabling EM extraction, and there is that group name, EM extract. Incidentally, you can have more than one extraction block and just send out parts of your circuit, so this can get quite sophisticated. How do I know I'm doing this right? If I click, notice that the elements turn red, which means they're ready to extract. And let me show you the layout here too. If we go to the left, My Stub, View Layout, notice that the layout of the T is red. It will extract out to EM. What about the ground flood? It's not going to extract right now. Well, we can fix that. I select it, left click, right click Shape Properties, and under Shape Properties, notice EM Extraction Options Enable, and there's that same name, EM Extract. And I come back, I select, and now when we look at the layout, it too will extract. Well, we're about ready to run our EM simulation, but before we do, there's a couple things I recommend. This, of course, will be a very quick little job, but if you had a complicated circuit, your EM could take quite a while to run. And how do you know you set it up right and make a mistake? One easy thing to do is right-click on the extract block, add extraction. And this now shows us the EM. Notice 2 ports have been added. These are where the ports were on the schematic, and this is ready to EM up. I can look at the 3D view of EM by going to the top and clicking on the box. And this is the EM. You might be asking, why is it in a box? I thought Axiom wasn't in a box. There's no top. It's not. But we simply put the box there to show you that you are an EM because we have another 3D view which is not EM. And furthermore, the box allows you to see the various dielectric layers. This looks good to me. It looks like it's hooked up right. It brought in the ground flood, and it's ready to roll. I'm now going to go over here to the left to the project browser, and you can see EM stub has been placed under EM structures. I'm going to take EM stub, right-click, add annotation, and in particular we have EM mesh here. It's all ready to go. I'm just going to hit the OK button. And you can see what we have going on in the 3D view now is it actually is meshed. This looks like a pretty decent mesh to me. The red and the blue, the 2 different colors, are because it's also showing you the DC connectivity when this is correct. So you can easily see if you have accidental shorts or opens. I'm going to go back over here to the left to this information button, and if I click on that, I get the number of meshes, and we can see that it's right now at about 1100 meshes. I have a quad-core computer. Axiom will use all 4 cores, and so this is going to take a few seconds of frequency point. Be a very quick simulation. Furthermore, we're running AFS, Advanced Frequency Sweeping. It's not going to simulate at all 101 points. Rather, it'll just do the smallest number possible to get a good approximation for all the data points. So we're ready to roll, and I'm ready to hit the Simulate button. EM has finished simulating. I didn't bother running the video while it was. It took 1 minute to simulate 18 points, so it was about 3 seconds of frequency point. And the graph here now for our S parameters from the schematic has been updated, so these are with the EM results. You might be wondering what was the old model results to compare. There are a number of ways to do this. One simple way to do it for a quick and dirty comparison is if I go up here to Graph, freeze traces, notice the traces have grayed out, go back to the schematic, right-click on the extract block, and disable it with our toggle enable. And now if we go back to the graph and hit the Simulate button, it is using the models. And you can see the differences here, and in particular, when we look at the S11 up in this range where my cursor is, you can see there is quite a difference. What's the difference from? Well, we had that ground plate, and also perhaps some of the models aren't as accurate as they maybe should be, because after all, those were pretty wide lines for the T, etc. Well, I hope you got a little bit of a flavor for our software from this quick tour, and that it gets you going. We have plenty more training out there. I urge you to take a look at it. Thanks again, everyone. I hope you all have a great day.